into our next session, which is based on research with tools and experience in PVC. And our first talk is by Prasun Dewan from UNC Chapel about leveraging Valgrind to assess concurrent testing and IEEE programs.
Thank you. Okay, so this long title describes work that my undergrad student Nalin Gaddis did with me as an honors thesis. So this is about testing. Chiranjeev, thank you for introducing that subject. And that means really writing programs that check if a programming assignment meets its requirements. So why do you want to do this automatically rather than manually? The obvious reason is that it's more reliable than error-prone humans. It supports more scalability, and it gives faster response. Okay? So that's good for short duration training sessions. A more interesting advantage is that as students build their programs, they can keep incrementally testing their programs, and the tests act as guides, helping them with the requirements, telling them where they're going wrong, and telling them where they're going right. Okay? Even more exciting, the tests they run as they're developing their programs can be logged and visualized, and instructors can tell how the class as a whole is making progress, who's falling behind, and who might need direct help from them. Okay? So you can get awareness of what's going on through test executions. Okay? So this is what tests can do. Let's go and see how tests would work. The traditional approach is that a test goes and runs the program with some input and checks whether the output meets the program requirements. And that works fine for sequential programs, but in the case of concurrent programs, we need to know, we can't just look at the results to tell whether it was concurrent or not. We need to see what parts of the algorithm were executed by what threads. Okay? So to handle this extra problem, my group has been working for a few years on developing solutions that essentially make assumptions about the program being tested. And one assumption we make in a solution that we developed a few years ago is that we are using Java. And the application consists of observable objects. These are objects that go and announce their state changes to anyone interested in them, any observer interested in them. Okay? So if the application is coded in this way, we can create an infrastructure that goes and traps all the state changes that have been announced and provides high-level abstractions to problem-specific checks so that they can be easier to write. And we found that this works well for visualizations that simulate some real-world activity, okay, that use observer objects to do the simulation. So what if you don't have a GUI and don't have a visualization? What if you have boring console output? For that, we developed a separate solution, which essentially requires tracing output to be generated by the application. Okay? So the application has to go and announce, print out state changes it's making, and these can then be, and so one sort of possible disadvantage of this is that the application is testing aware. The tracing output would not be generated if it was not being tested. Okay? So it knows that it's being tested, and I'm going to argue later that this tracing output is good anyway, but it is required for the test. Okay? And since we're working in Java, we assume that output is generated by making print method calls on a system out object. Okay? And in Java, you can change the system out object without the application knowing it. So we've changed the system out object to be an observable out object, which announces everything that's been output to anybody interested. And this way, we've been able to couple this with our previous framework and allow the benefits of that. And to even make programs easier to write, many of the problems we've been testing in our classes involve fork join. So we've developed special abstractions to support the fork join algorithm. Okay. So this all works pretty well if you are working with Java, which is what I personally do. But every time I present this work, somebody says, "But I work in C." So what I'm going to talk about today is how to handle C. Okay? So we're going to go and now assume that the process being tested is a C process. Okay? And we will, as before, create trace output. Okay? But this time, the tracing is not done by the program being written. The program is testing unaware. This time, the testing is being done, the trace output is being generated by wrappers that we create um, that intercept these function calls, and we use Valgrind to create these wrappers. Okay? So there's a high-level language to specify which calls you want to trap. Okay? And once you've got the trace output, you can go and analyze it in any language you want. Okay? So being fond of Java, we've developed special abstractions to go and parse this trace output into Java internal objects so that the tester doesn't have to go and do this work, and also to build a GUI around this, that is a testing GUI. Okay? And we've added a very simple library that simply counts in the trace how many times a particular call was made. Okay? And on top of that, we built some problem-specific checks. Okay? So this is the abstract picture of a system, the system we've created. Let me sort of show you concretely what these components look like. So here's a specification of what calls to go and trap. And we specify the name, the arguments, the result type. And based on this, we have a code generator that generates a wrapper. And this is for the lock call. And it goes and makes a call and then calls a trace method to go and actually generate the prints. Okay? And here's an example of a trace that's generated. This is an example of output that's generated. Some of the output is generated directly by the program, and some by the traces. Okay? So the traces go and print out the current time, the thread that went in, invoked that call, the name of the method, the arguments, and the result. Okay? And here's what our Java parser does with this trace. It converts all these fields into a data structure that you can then process later. Okay? And here's our call counting routine. So Valgrind trace is so it takes a function name, the minimum number of times the function is supposed to be called, the maximum number of times. It goes through all the past traces, figures out how many times it was called, and this is generic. And here's a special grader you've written, which goes and says, okay, I want pthread create call to have been called twice, and the pthread join to have been called twice. And if that's done, then a GUI goes and shows that did happen. Okay? And I'm showing you this detail here to show that testing in general is difficult. Testing concurrent programs you would consider is even more difficult. But here we have 5 lines to go and at least do this test. Okay? And this is something you can write. Okay, so this is the tool. And let me go and illustrate how you can use it for education. Okay? And I'm going to take as an example a producer-consumer problem. Okay? And this is about the simplest producer-consumer problem you can imagine. It involves the use of a counter. And that counter is going to be used to go and print out the first n integers in increasing order. Okay? And to make things interesting, the producer goes and increments, the consumer goes and prints, and we want to make sure that they take turns. So before before incrementing, the producer waits for his turn. Before printing, the consumer waits for his turn. And after incrementing, the producer signals the consumer, and the reverse happens also. Okay? And you put this within locks, lock and unlock calls to make things mutually exclusive. Okay? So if you do this, you're reliably guaranteed to get these numbers in sequence. Okay? And if you do it n times, you'll get n numbers. This is the same output you would get if you wrote a loop that in one thread that simply incremented, printed n times. Okay? So you can see that by looking at the result, you don't even know whether somebody did it single-threaded or multi-threaded. Okay? Leave alone whether they use lock and signal and so forth. Okay? So that is why we need traces. So what I'm going to do next is show you how our tests and traces can be used to evolve to go from the sequential program to this concurrent program. Okay? And I'm going to do this in stages. Okay? So teaching all of these primitives at once is of course going to be difficult, though I've never really taught pthreads. I can imagine it would be. So you would first go in. So I've got one version that just involves create and join, then one that involves also sleep call to do switching between the producer and consumer, and then lock and unlock, and finally also wait and see. Okay. So let's say you've got a sequential program, and the goal is to produce a parallel version where the producer is the one that increments and the consumer is the one that prints. Okay. We are not doing any synchronization right now. Just simply allow two threads to do the job. So if you take the sequential program and feed it to a grader, it says, oh, I was expecting pthread create at least 2 times, and we got 0 here. Okay? So you can tell that the sequential program is not correct. Okay? And if you do it right, you get a trace, and you can see that we've got pthread create twice here. And so the important point I want to indicate is that you don't really need to run the test to see whether you're on the right track or not. You can just look at the traces. The traces were meant to be a means to achieve testing, but they also become an end in itself, that you can really understand what the program is doing by looking at the traces. Okay? So if you notice here, I got all zeros. I didn't get 0 to 9. Okay, and that's because once the consumer starts printing, it'll keep printing and not give the producer a chance to increment. Okay, there's no synchronization. So if you really want, so the next stage is that after each increment, the producer sleeps, and after each printing, the consumer sleeps. Okay. So if you take the original program and feed it to a tester, it says, oh, no sleep call. Okay, though you did do something right, you got the create and the join calls right. And once you get the sleep version right, you'll see that we've got sleep calls traced in the trace, and the student can figure out that they're on the right track. Now, notice here that even so what the sleep call did was context switch. Okay, after each increment, there was essentially a thread switch to the other thread, and so they took turns, almost. Okay, you see that 8 has been printed out twice because this is not a reliable way of doing synchronization. Okay. So if you want reliable synchronization, we will use locks now, and we've got 2 locks. Since there's only one producer and one consumer, we can do without signals here, conditions here. So we've got one lock for the producer and one for the consumer, and the producer waits for its lock and unlocks the consumer, and vice versa. Okay? So this is how they take turns. And again, if you run the previous version, it says, yeah, you got some sleep calls, you shouldn't have any sleep calls, and you don't have the right number of lock and unlock calls. Okay? And again, the trace will tell you whether you're on the right track. So here we have the consumer waiting for its lock, and then after printing it out, it goes and unlocks the producer's lock. Okay? And finally, we can go to the and so the problem with that version is that it requires exactly one producer and one consumer. So what if you want multiple producers and consumers? Well, now you finally go to the program I started off with conditions. Okay, and again, if you feed the previous program to this, grader complaints, and here you again and see in the trace that the right thing is happening. Okay, so this is, I've illustrated a series of evolutionary concurrent examples, and since I don't teach C, I don't teach pthreads, I have not really exercised them in a class, and so this is all for illustration. So what I'll do next is show a case study, talk about a case study involving a real assignment. So this assignment was given an operating system class in which they simulated an LRU cache. Okay? And the cache was really a linked list of nodes. And each node had a key that represented the object being cached, a reference count being that how many times it has been accessed, and a lock to provide mutual exclusion to manipulations to that node. Okay? And we had a bunch of they had a bunch of referencer threads that went and incremented the reference count. So each referencer basically chooses a random key. If that key is not already in the cache, it adds it to the cache. Otherwise, it increments the reference count. Okay. And then there were a bunch of cleaners, and each cleaner was a thread that again chose a random key, checked if the key was in the cache. If it was, it decremented the reference count, and if the reference count went to 0, it freed it. Okay. Now, and they used the node locks for mutual exclusion. Now, the references can't do their job if the cache is full. The cleaners can't do their job if the cache is empty. So there was a count kept of how many elements there were in the cache, and there was a high watermark and a low watermark. And a referencer waited for the count to be less than high watermark before they tried to reference. And cleaner waited for the count to be greater than low watermark before it cleaned. And the referencer went, if after adding a node, if the count went above a low water mark, the referencer went and signaled the cleaner, and the cleaner similarly, when it cleaned up, if it lowered the count to below the high water mark, it signaled the opposite. Okay. So this was the assignment, and also there was a global lock to basically for mutual exclusion. So I've got some text here. Sorry. So there's a global lock for the weights and signals. So this problem is very different from the one I talked before. So I ran this program. This is not my assignment. This is some other professor's assignment. And I ran a trace of a particular correct solution, and we had 17 million lines in that trace. So clearly we need to filter out some of these things. Okay. Also, this is not as deterministic as the traces I showed you earlier. There was no regular pattern because of thread scheduling, non-determinism, random key choice. So there were variable number of locks, and for a lock there were variable number of mutexes, and for each mutex there was variable number of lock and unlock. Okay. So it's not practical or even possible to identify all possible invalid traces. So writing tests based on these traces is difficult. Okay. And so the student who built Valgrind++, which is sort of the system I talked about, was also the TA for this course, and he had graded assignments, and he knew what kind of mistakes people make. So based on these mistakes, he actually wrote some tests, and one mistake people made was that a referencer would go and just signal the one cleaner and vice versa, where they had to actually broadcast. Okay, so that was a mistake that people made often. And so he had a test to check that. Okay. So there were 53 assignments initially graded manually. And assuming this, they didn't really time these students, the grading. But assuming it took 5 minutes, which is pretty conservative, it would have taken 4 hours to grade those 53 assignments. Okay. And this is kind of cheating because Nalin was also the builder of the system, but it took him 2 hours to go and build the tester for this. Okay. And he correctly graded. I mean, this was still not checking for everything. Okay, and he correctly graded 46 out of the 52. I guess 53 it should be. Assignments, and got 11 errors in manual grading. So that showed the use of tests. And also, this is an interesting point. More than half the class did not implement node locks. They just had the global lock, and they didn't do the fine-grained locking. Okay, so people talk about providing help for the novice students. These are students who are in a 500 level course, and they have had trouble. Okay, so that's one of my sort of points that we need to also address the more advanced students. So what have I tried to say today? One lesson here is that Valgrind offers, can be used to generate traces. Okay, and I've told you how we did it, and something you can do it too. How, even though you have traces that can be used to check for almost any condition you want to, checking that is difficult. Okay, so you have to use some knowledge of what kind of errors are being made, okay, to write your tests. And also, I like this producer-consumer problem and its evolution. And like I said, if I was to ever teach B threads, I would use that, and I'd love to sort of see that be done. And the initial data from the case study shows that automation offers benefits. And like I said, even advanced students need help. Okay? So what's the most interesting to me is what's left. Okay? So I've shown through the case study that we get the scalability, reliability advantages that checks I said would get. Okay? But how about actually making, and this is sort of what's missing from our work, this tool was not actually used while the students were building their programs. This was a retrospective study where we took the assignments and graded them later. How would things have changed had they been using it? Okay? So that's sort of one thing. We can study logs to understand how tests influence programmer actions. Okay? And I think this is a rich area for education. That yes, tests are good, and manual tests might do the job, but you really don't know what's happening. You really want to know where people are having trouble. Give them tests, log them, and check what's happening. Okay? And so that's the other part. How are the students reacting to checks, and how can you visualize that execution and adapt your work to adapt your assignment or provide help. So that's sort of an important area to pursue. Okay. Also, like I said, it'd be good to go and give this in the actual class. And not only this, I mean, if you have P-thread assignments or any C-based assignment really that you want graded, we have a system for it. We have a system that logs things. We have a system that visualizes things. So there's a rich amount of data you could get if you use the system. Okay? That's part of the reason I've come to this workshop to sell this stuff. Okay? At this point, we have 3 independent frameworks. I have this Java framework, which has this observer-based generic high-level abstractions. I've got this Valgrind++. And there are also tools that do problem-independent checking. These tools I'm talking about do problem-specific checks. But what about some general problem-independent checks that like Valgrind provides? So we're good to sort of integrate these frameworks in some way. Okay? And actually, I'm working on that. So that's it. This is just something I did in text and I replaced with graphics, and I guess I'm ahead here.
Let's thank the speaker. And we have time for questions. While you're thinking, I have a question for you. If suppose I was to give this to my TA for grading program assignments, what is the learning curve for that TA?
The learning curve will be high. It depends on what kind of documentation I provide with you. So what I would do is have them sort of talk to somebody like me or Nalin. But once somebody, they have to write 5 lines of code, right? So if I give them the 5 lines that we've written and they have to just modify that to their word, it's not. Okay? But if they want to know how it was done to first principles, that's. But like I said, writing 5 lines of code is never going to be hard ultimately. If you're satisfied with call counting.
Really interesting session. Thanks so much. My question is, you explained how Valgrind can be used multi-thread application. So is there a feasibility for this to be used for multi-node, for example, MPI?
So MPI?
Yes.
Yeah, why not? All we need is a library. Okay, if a standard library that the program application is using. Okay, and we can go and trace every call to that. So in fact, I want to use for MPI, and haven't tried it for MPI, but then you'll have to take traces from multiple processes and analyze them together. And I teach distributed computing with Java, and we actually go and combine them all into one. We have one process that goes in. We run them all on one computer, and we sort of go and combine them, and we go and separate them out. So I've got a bunch of tests written for map reduce problem and other things we do use using Java RMI. So the same thing can be done with MPI. Absolutely. Yeah.
You can see the things very controlled. So please, have you looked at log free code?
I haven't even heard of it. What is it?
lock-free code, wait-free code. So the counter you.
Oh, lock-free code.
Yeah, right.
Oh, sorry. I thought you were talking of some buzzword here. Uh, so, why do you ask me this question?
Well, traces are important, right? Because if you throw in the box and if you observe the traces, that will depend on how the hardware orders memory operations, right? So X-series has certain model, or it's very different. So you could have your DA look at traces on the X-series installed on Dell machine. Students might use Apple M1 and 2, which is all space, will order the order operations differently. Locks won't have a problem because lock acquisition events and resets force caches and everything together.
Right. So here's the deal. Lock-free from what I remember. Okay, basically replicate data. Okay, so when you the thing that you would do in a single cell, you go and replicate that in an array, and each process goes and accesses its own node. Okay, that's my knowledge of lock-free code. Okay.
Right? You use a calling instruction like we want to write the parent swap to fetch and whole range of instructions. Maybe we can take this.
Right. No. Hang on. I don't. I got time. so the point is that we are testing what the programmer is doing. Okay, we're not testing what's happening underneath there. Okay, so if what the program does causes all kinds of non-determinism, that's exactly what I showed you happened with the case study. Right? There's just so many combinations of traces that can happen.
You could do that when your code uses locks, because the memory ordering operations by the hardware will enforce a certain order, right? The locks are required at least. Not so much where the code does not use locks.
Right. So again, the issue is whether the programmer is doing the right or the wrong thing, right? So if there was some library call, the programmer had to execute towards a correct solution. Okay, towards a correct solution. We can figure out whether the library call was made or not. That's all we do. Nothing else. Okay? So if you just write a sequential program and underneath, that ISI person who gave a talk today and is going to paralyze the hell out of it, you didn't do anything. So you didn't do anything wrong today or right. You didn't do anything wrong or right. So we can't check that. We can only check whether you as a programmer made the right library calls. That's all we can do. And it doesn't matter what the library is. And underneath what's happening, we can cause problems because it can cause non-determinism. And that's kind of the problem I showed with you with that LRU cache.
Yeah, but I could write correct log free code and say this, which might be incorrect or wrong, and your DA will get a meaning, right?
It may be you can write correct.
Correct log free code and say this, all will be ordered and the log is correct. And if you trace this, it will.
So again, we are just looking at library call executions. Okay, and we're not looking at. Yeah. Okay. So we're not looking at instruction execution, just library call executions. Just remember that. So we don't have that much knowledge of what's happening. We're not tracing every instruction. And if there is a pattern there, you can write tests for it. If there's no pattern, no help. That's okay. We'll take this offline.
Are there any other questions?